If the universe is as we think it might be, a sort of closed system surrounded by a horizon, and that horizon behaves roughly like the horizon of a black hole, any self-contained system, if it satisfies any kind of version of standard laws of physics, entropy will increase until it comes to thermal equilibrium. Once it comes to thermal equilibrium, not much happens. Thermal equilibrium is extremely boring. It really is a dead world.
However, the classical story of the increase of entropy misses part of the evolution.
Quantum entanglement is still evolving. Things keep happening.
We proposed the second law of quantum complexity in direct analogy to the second law of thermodynamics.
This is a really provocative suggestion.
It struck me as something that did not compute.
They came to the conclusion, old Lenny used to be a good physicist. He got into this complexity story, but he didn't know what complexity was. My friend, who was my friend and a good friend, Feynman, he would close his eyes and visualize a system. And then when he had a visual picture of it, he would convert that to mathematics. I don't have the mind of a mathematician. I have the mind of an auto mechanic. What works is what's practical. But sometimes you need some mathematics. I learned about black holes. And there was something about black holes. It had nothing to do with complexity at that time, but there was a puzzling feature that I didn't understand. We had these pictures, they were called Penrose diagrams. It's a kind of map of the whole universe, including a black hole. The black hole is over here, time goes upward. The interior of the black hole had this strange behavior. The interior of the black hole came to a smallest size and then expanded. It bounced and it started to grow. And I didn't know what that bouncing thing was. And I gave up. I didn't know what to make out of it. I would ask my friends, what's growing here? What's the black hole experts? And they would, I don't know, it's just the volume of the black hole. Okay.
Entropy was invented by people during the Industrial Revolution who wished to understand the maximum possible efficiency of steam engines and other similar machines. And what they were interested in was the entropy of the working gas in their engine. So this was both an important theoretical understanding and also big business. That is the story, though, of entropy, a statistical claim that this disorder of the system always increases.
I knew that it wasn't entropy because the entropy of the black hole comes to thermal equilibrium very quickly. On the other hand, you can look at the Penrose diagram and you could see that expansion lasted for a very, very long time.
So if you start with black coffee and milk and mix them together, it's not going to take very long before you in fact have, at least as far as the intermixing is concerned, thermodynamic equilibrium. And in fact, it'll look, at least as far as thermodynamics is concerned, like the arrow of time has stopped. The thermodynamic arrow of time has ceased. The system is now in a heat death situation. There is no longer any ability to generate more entropy. However, that is not the end of the story, because even though the system has reached thermodynamic equilibrium, it has not reached complexity equilibrium.
Feynman taught us that the number of quantum states of a system is enormously large. If you have a certain number of qubits, the number of orthogonal quantum states of that system is exponential in the number of qubits. What that means is that, for example, a quantum computer or just an ordinary system will take an enormously long time to explore the entire space of states. It'll start out at some simple state and start wandering around in the space of states much, much longer time than it takes to establish thermal equilibrium. All of a sudden it hit me, bang. The complexity of a quantum state just increases and increases and increases long, long past the time when the system has apparently come to thermal equilibrium. And that this size of the interior of the black hole was a direct measure of the complexity of the quantum state of the black hole. When that hit me, I suddenly got really, really interested in the concept of computational complexity.
So a classical system, we basically can describe it like, oh, I have a bunch of bits and they can be 0, 1, 0, 1, right? I can just describe them individually what state they are. But for quantum system, that's not enough. We cannot describe the system by starting from the first qubit and then describe the second qubit, because they can be globally entangled, and locally there might not be information at all, but globally they might be in some highly non-trivial quantum state.
Entanglement is the key to why complexity can grow so large for a quantum system.
I first heard that there was a connection being drawn between circuit complexity and black holes way back when I was in grad school, when Leonard Susskind and his collaborators made the suggestion that circuit complexity might be playing a role in understanding quantum gravity. And when you first hear this as a computer scientist, this is a really provocative suggestion.
Lenny had formulated this, and I happened to be at that talk. And what I found hard to believe about it is that he was equating something that is physical, volume, with something that, as a complexity theorist, I would say, this is quite unphysical, quantum circuit complexity. That's something that's manifestly hard to compute.
I'm not sure we had a particular hypothesis, but something felt funny. The states that Susskind and his collaborators were considering actually look a lot like a quantum analog of a block cipher. Funnily, after this long period of exploration, our work ended up in some roundabout way justifying Susskind and collaborators' conjectures. That was a really unexpected result of our investigation.
We realized that rather than reinforcing our skepticism about his proposal, what our results suggested was that, in fact, that was the only sensible way to resolve the paradox. So that was a really interesting thing, that he had this deep intuition. It's pretty remarkable.
Eventually we just said, let's put forward the idea. The computer scientists had never put it forward, they hadn't said it. Let's put forward the idea that there's a second law of complexity, that complexity behaves very much like entropy and always on the average increases until it maxes out.
We proposed the second law of quantum complexity in direct analogy to the second law of thermodynamics. I would say that it is not a law in the sense that it's been proved. It is a conjecture that there should exist such a law, but the analogy with the classic second law of thermodynamics is sufficiently strong that we felt emboldened to propose such a law.
At the moment, I think it's something which really applies to black holes. The extent to which it applies to the universe as a whole is not entirely clear.
So this idea of using quantum circuit complexity, this is treating quantum system in a quantum mechanical way, rather than starting from a classical starting point and do some semi-classical approximation and then bootstrap from there. That can take us somewhere, but it's not all the way. So once we accept that the world is quantum and we fully embrace that, then we can actually understand things much, much better, because we're now standing inside the quantum world and we're using fundamentally quantum language to describe it, as we should have for a long time. And that will be a fundamental change of how we think about these kind of systems.
What the implications of complexity growth are for the evolution of the universe. At the moment, this is unexplored territory.
Eventually, if you wait an exponentially long time, even the quantum complexity achieves its maximum value. Even the quantum complexity reaches its own analog of heat death. And there maybe the story begins again.
As people say, if you wait long enough, everything will happen, including what you started with.